Hello and welcome everybody to the Graph Theory Seminar at Georgia Tech. Our speaker today is Songling Shan from Illinois State University, and she will tell us about the chromatic index of dense quasi-random graphs.
All right, so thanks Anton and others for the invitation. So I'm really happy to be here to share this with you. So I will start with some of the concepts related to overfull conjecture, and then we will talk about overfull conjecture for dense quasi-random graphs. And then I'll talk about the proof outline, and I have some open problems at the end. So let's start with some concept. When we talk about edge coloring, so it just means an assignment of colors to the edges of the graph so that incident edges, they receive different colors. Because for any two edges, they receive the same color, then they don't share any endpoints, right? So from here, we see that a color class is just a matching. So a color class is just means the set of edges with the same color. And when we talk about edge k coloring, just means an edge coloring, but we're using color, the integers from 1 up to k as the colors. And the chromatic index is the smallest integer k such that G has an edge coloring. And one using observation is that the chromatic index is always at least the maximum degree of the graph. And here is an example for the for edge four coloring for the Peterson graph here. And for simple graph, on the other hand, we then prove that the chromatic index is at most maximum degree plus 1. So from here, we see that for all simple graphs, they can be partitioned into two classes. For class 1, if the chromatic index equals the maximum degree, and otherwise we say it's class 2. And Hollier in 1981 showed that actually it is NP complete to determine whether an arbitrary graph is class 1 or class 2. So, but in some of the cases, we do have a sufficient condition to determine if a graph is class 1 or class 2. So mainly that if the graph has too many edges, then the graph has to be class 2. So by too many edges, we really mean that the number of edges is bigger than maximum degree times number of vertices divided by 2. So because in any graph, a maximum matching can contain at most half number of the vertices, right? So if a graph has this many more edges, then we need more than delta G colors to color the edges. And another observation we can see from here is if a graph is overfull, the graph must have an odd number of vertices. And for some examples for overfull graph, like odd cycles, those are overfull graphs, and the regular graphs of odd order, right? So particularly complete graph and odd number of vertices. And also if you have a regular graph which has an even order, but if we subdivide one edge, then that graph will also be overfull. So not just the graph itself overfull, then the graph is class 2. Also, you can think that if the graph has over delta G overfull subgraph, just means a subgraph which has maximum degree delta G, and that subgraph is overfull. So only edge coloring that subgraph, we will need delta G plus 1 colors. So this means under that condition, the whole graph will be class 2 also. So as here, containing a delta G overflow subgraph actually is a sufficient condition for a graph to be overfull. But this sufficient condition is not necessary. So one example is this Peterson graph. If we delete one vertex, after deleting one vertex, we call that graph P star. For the graph P star, which is class 2, we still need 4 colors to color the edges. But P star is not overfull. It has 12 edges, right? And the number of vertices n, which is 9. So you can calculate the P star is not overfull. So containing delta G overfull subgraph is a sufficient condition for a graph to be class 2, but not necessary. So then we might ask, under what condition can this containment of delta G over subgraph be both necessary and sufficient for a graph to be class 2? And this question actually was conjectured by Chetwynd and Hilton. So the conjecture says that as long as the graph has a larger maximum degree, then the graph is class 2 if and only if G contains delta G over 4 subgraph. And for this conjecture, you see that one of the direction is pretty obvious, right? So contains delta G over subgraph. Usually this implies that the graph is class 2. So the hard part is to prove the other direction. Assuming that we have such a graph that is class 2, you want to show that the graph contains a delta G over 4 subgraph. And there are some implications. Oh, right. So one more thing to say that this condition in this overfull graph conjecture is best possible. Again, you can see this by the P star. And this P star is one example to show this sharpness of this degree condition. But actually, this is the only known example to show the sharpness. And this is only a finite graph. So it's really don't know that, for example, if your graph has many vertices, probably maybe n over 4 or even something smaller could also satisfy the conclusion. So there are many implications of the overfull conjecture. One thing is like once the overfull conjecture is true, then for graphs with the maximum degree greater than n over 3, we can always find a polynomial time algorithm to determine the chromatic index. So recall that this problem in general is empty hard for a general graph. And why this is so, and this was a result proved by Nissen in 2001, saying that for graph, if the maximum degree at least n over 3, then it has at most 3 induced delta G over 4 subgraph, and it is possible to find one in polynomial time. And if the maximum degree is at most at least n over 2, then it has at most 1 induced delta G over 4 subgraph, and it is possible to find one in linear time. So actually, for this second case, if the graph has an even order, then the only possible delta G over 4 subgraph is obtained by deleting a single vertex. And if the graph has an odd order, then the only possible delta G over 4 subgraph is the graph itself. So actually that is one of the reasons that the overfull conjecture implies the one factorization conjecture. So anyway, I will talk about this later, but we need those concepts. So we say graph G is delta critical, just means the graph is class 2, and any proper subgraph will have smaller chromatic index. And we say graph is just overfull, just means that we have exactly one more edge that the graph not being overfull. And the overfull conjecture actually implies those conjecture. The first one is this one factorization conjecture. So why this implies a one factorization conjecture? Because n is even, the graph is regular, right? So as I mentioned before, the only possible overfull subgraph is by deleting one vertex. But as the graph is regular, if you delete one vertex, you can think that we delete actually delta these many edges. The remaining graph is not going to be overfull. So naturally, if we have uneven and the degree k is at least this many, and then the graph has no overfull subgraph. So it is one factorizable. And the other conjecture, splitting vertex conjecture. This conjecture is just saying that if you have a degree is greater than n over 3, and the graph is obtained from a k regular class 1 graph on n vertices by splitting a vertex, then this graph is delta critical. So here splitting vertex is just means that like if we have a vertex U, we can split this vertex into 2 new vertices, call this U1 and U2. We will add an edge between these 2 new vertices, and then we will split the incident edges at U between these 2 vertices. You can split it in arbitrary way, but make sure the degree of U1, U2 is at least 2 in the new graph. So this conjecture is just saying that if we have a graph obtained from a k-regular class 1 graph by splitting a vertex, then the graph is a delta critical. Since such graph is class 1 and regular, so it has an even number of vertices. And if we split U into 2, the graph is definitely overfull. So that already proves that the graph is critical. Is class 2. So to prove that it is delta critical, basically you need to show that when you delete every edge, that will decrease the chromatic index of the graph. And another conjecture, this is just the overfull conjecture. This is also implied by the overfull conjecture. So this one saying that if we have a graph G of order n, and the maximum degree at least n over 2, then G is delta critical if and only if G is just overfull. So for the overfull conjecture, it's proved for some special classes of graph. So for example, it's proved for graph if the maximum degree is big, about n-3, and it was not even proved for delta G at least n-4. And Planhold, he proved that when n is even and the minimum degree is big, then the overfull conjecture is also true. And recently, he improved the minimum degree to 2n/3, actually by applying the result from here, the one factorization conjecture result. So for this one factorization conjecture, as I mentioned before, this is a special case of the overfull conjecture, and it was proved for large graphs. And also for graphs with maximum core degree 2. So here for the core degree, for a graph, we can define its core, call this G of delta, to be the subgraph induced on the vertices of maximum degree delta. And if the core, the maximum degree of this core is at most 2, then all such graphs actually, if they are class 2, then they will be overfull. So this is a joint work with Chhetwynd and Hilton. We did this in last year. And this, the next one, so this is for minimum core degree 2. So actually, for all graphs which class 2 graphs with maximum core degree at most 2, those graphs, they are actually delta critical with delta at least this value. So based on that work, we showed that if the minimum core degree is 2, is at most 2, and the graph delta critical, and with delta greater than n/2 + 1, then the graph itself actually, if it's class 2, then the graph is overfull. And then recently we can prove that if we have a critical graph, so delta critical graph has order n, and the maximum degree is much bigger relative to the minimum degree, then the graph itself is overfull. So now let's move on to the overfull conjecture for quasi-random graphs. So about fine. It's weird. Actually, I have a page here. It's just missing. So anyway, this page was supposed to be some copy from the Wikipedia. So which are all the equivalent definitions for quasi-random graphs, like the definition in terms of the discrepancy. You counting subgraphs, counting 4 cycles, and also like the eigenvalue bound, all those different equivalent definitions for quasi-random graphs. And for here, so when we will consider the one-sided version of epsilon regularity. So epsilon and p will be real numbers between 0 and 1. We say an n-vertex graph is lower p epsilon regular if the number of edges between any two disjoint large vertex set is at least p minus epsilon times the size of s and times the size of t. So we require size of s and t to be at least epsilon n. And this was one result by Glock, Kühn, and Osthus. So they showed that if the difference between the maximum degree and minimum degree is small, so about delta of n, and if we have a lower p epsilon regular graph, but require n to be even, then the overfull conjecture is true for such graphs. And they actually, in their work, they showed that it's possible to find a polynomial time algorithm, so to find such an optimal edge coloring. Then so this is the definition for quasi-random graph. Just the one-sided version for the epsilon regularity. And this was the result by Glock, Kühn, and Osthus from 2016, showing that as long as the graph has an even number of vertices, and the difference between the maximum degree and minimum degree is relatively small, then the overfull conjecture is true. And in the same paper, these authors, they asked that, actually they conjecture that the same should be true for such graphs of odd order n. So recently I proved that actually their conjecture is correct. So then for the, about this, so recalling that original result when n is even, they said it's possible to find there's a polynomial time algorithm to find an optimal coloring. But for this here, I am not sure if there is a polynomial time algorithm to find an optimal coloring. Because in the proof, I need to partition the set of vertices into two parts, and a light partition was guaranteed by probability. So I'm not sure if there's a polynomial time algorithm to find such an optimal edge coloring. And the other thing is, if you see this statement, instead of saying that if and only if G contains no delta G over 4 subgraph, I just say if and only if G is not over 4, because for such lower P epsilon regular graph, if the only possible delta G over 4 subgraph of G is just itself. So why this is so, basically, if we take any subset X of V of G, so suppose the size of X, which is at least 3, and at most n minus 2, right? So you can calculate, because the graph is lower P epsilon regular, so the difference between the maximum degree and minimum degree is small. So that actually implies that the minimal degree of the graph is at least like half P over 2 times n, something like this. So for any subset X, which has size at least 3 and most n minus 2, you can calculate the number of edges in G between X and the remaining set. So in other words, the boundary edges for X. So this number is always greater than or equal to the delta G. So this means the number of edges within X, this will be always less than or equal to X times delta G. So I should say 2 times EX, right? So delta G subtract delta G. So this implies that the graph is not going to be overfull. The subgraph of G induced on this set X is not going to be delta G overfull. So for such lower P epsilon regular graph on n vertices, when n is odd, the only possible delta G overfull graph is this graph itself. And then now go away. So now we will talk about the proof outline. So to start up, I will setting up these parameters. So I will choose the bound on the number of vertices, which is much less than epsilon, and eta will be much less than P. So actually, in particular, in the proof, eta is about, so this is like about p to power 4 something up to constant coefficient. And for eta 0, this is kind of like about 1 over eta to power 3rd up to a constant factor. So as I said, because for this graph, the difference between the maximum degree and minimum degree is small. If you do a little bit of calculation, we will see that the minimum degree of the graph is pretty big. So at least alpha n. So here we can set alpha to be about p over 2. And then we will assume that the graph G is not overfull, because if it's overfull, then the graph will be class 2, right? We already done, because this forward direction is clear. So we assuming the graph G is not overfull. So what we only need to prove is to prove that the graph is class 1. So the chromatic index of G is delta G. And to do the proof, because the graph only has an odd number of vertices, which is a little bit not good nice to work with. So for the first step, I will add a new vertex X to the graph. So I will add this new vertex and some edges in between to get a new graph G prime. So for this new graph G prime, I require that to have the same maximum degree. And this G prime, I call it a star multi-graph. So because, and I call X the multi-center, because all the multiple edges is between X and the remaining part. And then in step 2, we will take out linear forests. So linear forest just means vertex disjoint path from G prime to obtain a regular lower p epsilon regular star multigraph G star. So here epsilon prime is about square root of eta something. And then for this graph G star, we will show that G star is class 1. And then, so if we should G star is class 1, then we will color the linear forest we took out in step 2. For each linear forest, we can properly color the edges using 2 colors. So suppose if we took out k of them, then the chromatic index for this graph G prime, which will be at most this, and this is delta of G prime. And so the chromatic index of G, because G is a proper subgraph of G prime, will be at most delta G, right? And on the other hand, it's at least delta G, so it's exactly delta G. So actually this procedure generally follows the original idea of Glock, Kühn and Osthus improve this problem when n is even. So in their case, like when they get to the 3rd step, so because you have n is even and you have a simple graph, they use the result that such graphs have a Hamiltonian decomposition. So at that stage, if the degree of G star is even, then you have a Hamiltonian decomposition. Then for each Hamiltonian cycle, you color the edges using 2 colors. And if the degree of G star is odd, you just take one additional matching and Hamiltonian decompose the remaining edges. So that was their original idea. So for me, this is step 3. I have to develop something new because I have a multi-graph here. So now let's go to the detail for each of the steps. So for step 1, I will add a new vertex and some edges between X and the graph with those conditions. So the degree of X, this new vertex X in the resulting graph will be equal to the minimum degree of G prime, but also this the minimum degree of the original graph. And I require the 2 graphs to have the same maximum degree. And subject to 1, I want and most 1 neighbor of X in G prime, which is not a maximum degree vertex of G prime. So to do this is just by doing some analysis. Because the graph G is not overflow and n is odd, we can calculate that the sum of the degrees of vertices in G, which is at most delta times n minus 1. And then so for this inequality, if you move the delta n, well, just move this part to the right? And then So delta n subtract this, which gives you that. So this value, I will define delta subtract dg of v. We call this the deficiency of the vertex v in the graph G. So the sum of the deficiencies of all these vertices in G, it will be at least the delta of G. Because the graph G is not overfull, so it has large deficiencies. And then we suppose the vertices of G are x1 up to xn, and we order the degrees of this vertices in this way. And now I will take a small list. So just note that this vertex has to be the maximum degree vertex, right? Has the largest degree. So now we will choose smallest index as between 1 and -1, such that the sum of the deficiencies of those vertices is at least a third of G. And now we can just add the edges in this way, as I draw in this picture, then I will get this new graph G prime. So you can easily check that G prime satisfies both condition 1 and 2. So sorry, give me 1 second. Chart is talking.
No problem.
Sorry. So actually by this, so once we construct this graph G prime for the vertex X, this is the only special vertex we have here. So you can actually check that the number of labels for this vertex X, it might be a constant, but it is actually a big constant, right? Because we choose alpha is about P over 2, and eta is much, much smaller than P. So this constant could be a big number, but I write these 3 bonds because I will use this in the next step. So after we finish step 1, again, we can easily check that this new graph G prime, it contains no delta G overfull subgraph. So the same reasoning as before for any subset X of G prime. So if the size of X is at least 3, and at most n-2, you can check that this graph Gx, which is not delta G overfull. So for this graph G prime, the only possible delta G overfull subgraph is obtained by deleting only one single vertex. But then you see that since we constructed this graph such that the degree of X is the smallest, right? So if you delete any vertex Y, such that G minus Y is delta G over 4, that means G minus X, G prime minus X must be also delta G over 4. But we already said that G prime minus X, this is the graph G, which is not delta G over 4. So this whole graph G prime is not delta G over 4. And in particular, because it's not delta G over 4, the deficiency for the graph for X in G prime is at most the deficiency for other vertices in G prime. Again, you can just calculate this by use the fact that G prime contains no delta G over 4 subgraph. Because otherwise, if we have this, that means G prime minus X will be delta G over 4, but we assume that is not the case. So after this is step 1, then for step 2, we will take out linear forests from G prime to obtain a regular lower P epsilon regular star multigraph G star. And to do this, we will construct an auxiliary graph H on VG prime with the degrees being the deficiencies of vertices in G prime. So, and this is possible because as we analyze, we have this condition, and because the new graph G prime, it has n+1 vertices. So the degree sum is even, and n plus 1 times the delta of G prime is even. So this deficiency is also even. The deficiency is n plus 1 times delta subtracted sum of degrees, right? So this is also even. And now we can use a result of Hakimi, just saying that if we have such a condition, then we have such multigraph H, such that the degrees of this vertices in H are just the deficiencies of the vertices in G prime. So we can consider such graph H. And for this graph H, we will partition the edges into matchings. So each of the matching have relatively small size, and the total number of matchings is also relatively small. So from here, you see that because each of the matching has a small size and we have only a small number of matchings, after we took out something from the graph G prime, the remaining graph will still have a relatively large minimum degree. So we can have a good control of the remaining graph. And for the second part, why we can do this such partition for the number of edges, the edges of H, because the maximum degree of H, which is at most 8 of n, and the chromatic index by Wiesen's theorem, which is at most maximum degree plus the multiplicity of H. Multiplicity means the largest number of parallel edges between two vertices. So which is at most this, and then because the 2 eta n is less than 7 eta n divided by alpha, so we can greatly partition the number of edge, the set of edges of H in this way we mentioned here. So, and now we will took out the linear forest from graph G prime iteratively. So to start, take the initial graph to be G0, and the G1 will be G0 by taking off the first linear forest, etc. And here we require those linear forests. So each vertex of G will have degree either 1 or 2 in the linear forest. And the leaves of those linear forests are just the vertices of the covered vertices of each matching. So basically the idea is like, you can think maybe this is like the matching M1, right? So we have those edges. So those vertices, they all have deficiency, positive deficiency in the original graph G prime. So when we take out the linear forest for each of those paths, so it will, and for those vertices which have positive deficiency, they will only contribute a degree 1 in this linear forest. But for those vertices of the delta degree, it will contribute a degree 2. So you can just imagine, like after several rounds, we will make the graph into a regular graph, because the maximal degree vertices, the degree will subtract by 2 each time. But for those vertices of small degree, they will the degree will decrease according to the deficiency. So after this step, then we will eventually reach to a graph. We call this G star. So actually, which will be GK. So epsilon prime is setting to be about this parameter. And then take alpha prime is about 6 alpha over 7. Then we can show that the G star is a G regular, lower P epsilon regular symmetrical graph with this minimal degree relatively large. Then for the third step, so we will show that such graph G star, which is class 1. And after the third step, then we will color each of the linear forests using only 2 colors. And the H delta G star coloring of G star together with those 2K colors from those linear forests together, that will give us an H coloring of the original graph G prime using at most delta G colors. So this includes that the chromatic index of the graph G, which is the proper subgraph of G prime, is at most delta G. So I have about 8 minutes. So I will roughly talk about the idea for the third step. Am I right, Anton?
Sorry, you have even a bit more, maybe 12 or something like this minutes. You can go
Okay,
until
okay,
like
so
35 past, even, even 40 if you need to.
okay, so I should have enough time to explain this step. So actually, to show this step, the idea was used by Van Han when he did the work, the multi-graph version for the one factorization conjecture. So basically, it's about like you have a multi-graph. If the minimum degree regular, right? So regular with the degree d about r times half plus epsilon n. So here R is a multiplicity of the multigraph. Then such graph, for such graph, the chromatic index equals the maximum degree. So that's the work by Van Han. So the idea I used here is really to modify his idea from that work. So basically, for the first step, I will do a partition of the vertices of G. So, well, it's a G star, but I'm just saying it's a G into two partitions. Because this vertex X is kind of a special vertex. So from the graph, I will pull out this vertex X together with a vertex Y, such that X and Y, they are long adjacent in the graph G star. And then now I will have n minus 1 vertices. So n minus 1 is even. So I just try to find a balanced partition. So for this balanced partition, just to use the probability argument. So you can make sure that for each vertex, it has approximately the same degree in its own partition as in the other partition. So we get such a partition. And then after this partition, so, right. Let me still use this color. So after this partition, maybe I can assume that this vertex X, it has more degrees in this partition than the other. So now I will put this vertex and this vertex here, and add the vertex Y here. So this new one, this will be a vertex partition of the graph G star. So I call this A and B. So remember that for this vertex X, it has more degrees in the bottom partition B. And then, so now for the graph AB, I will consider a subgraph, which consisting of the entire graph above here and here, and together with some edges incident to X. So this is X, right? So it can happen that the X may have a really small degree in A. So I will add some edges to here. So the number of edges I add here is about the degree of X in this B, subtract the degree of X in A divided by 2. So adding about this many edges between X and B. So now in this graph, so the degree of X is about half of the degree of G star. And then for this green graph, so consisting of the up graph, the bottom part together with those edges, this graph is a star multigraph, right? X is a only possible multi-center. So for this graph, you can you can really show that. So by using Wisen-Fan argument, the chromatic index for this graph, namely called maybe G double star, whatever. This is about delta of G double star plus 1. So for such a graph, we will find an edge color and use about delta maximum degree of G double star plus 1 colors. And in such edge coloring, so we have this requirement. So it's almost like an equalized edge coloring. So like if the color 1 means 10 times in A, it will miss about 10 times in B. So it's kind of like an equalized coloring. So in particular, like for each of the colors, so for example, for the color, for a particular color I, it will miss the same number of vertices in A and also miss the same number of vertices in B, and the number of vertices missing this color in both A and B, they are equal and the size is pretty small. So now for each of those color, because they miss the same times in A and in B, I can pair them up, right? So like for this vertex, it misses color I, and here I miss I. So for each of these missing color, we will do a swap, use a capo swap, so that I can make sure this color I will present at this vertex. So basically, we will find an edge in middle, an edge in here, and in here you will find an edge which with the color I, and we will find here an edge with the color I. So because this graph is lower pi epsilon regular, minimum degree big, actually it's a big set satisfies this property. So there will be an uncolored edge in middle, then you do this swap. So the first, third, and fifth edge, those are uncolored edges. And then we have two color edges, we do this swap. So we do this swap for each of this pair. And after this swap, then let's say for the first part, we used edge maybe P colors, right? So those P colors will be becoming P perfect matches, so P1 factors. And now we introduced some of the uncolored edges in A and B. And for those uncolored edges, it's really a small size, but you can just, we will just color those edges. Again, when we do the coloring, because these two graphs, they are independent. Actually, in this process, we can make sure that the new uncolored edges we produce in A and B, they have the same number. So then we can make find an equalized coloring for those uncolored edges and those uncolored edges. And then, so for now, for each of the new color, like this one, this color, again, I call this color I. If it appears twice in the top, it will also appear twice in here. Now we will deleting those vertices which already present this color, and between this remaining graph, it's a balanced bipartite graph in the middle. You can find a perfect matching. So for those matching, we will color, like here you use the color I will color all those edges, use the color I. And after those two processes, so in the first process, we use the P colors. Suppose in the second process, we use the Q colors. After those two processes, we use in total P plus Q colors. And each color class is a perfect matching. And now what is left is only a regular bipartite graph in the middle, and which can be colored use delta G star subtrend P subtrend Q colors. And all those adding together, that gives you a proper delta G coloring for the entire graph. So the only thing I kind of didn't mention a lot of detail is the special vertex X. But the vertex X is only one, so just you do that carefully, you can make sure that everything will work out. So finally, I will talk about some open problems. So the first I mentioned before, can we prove the overfull conjecture for graphs G with n vertices and maximum degree equal to n minus 4? And the second problem is, what about for the overfull conjecture for graph G on n vertices, which has a large minimum degree, so about n over 2. So like if you require delta to be about maybe half plus epsilon n, and the difference between delta and delta maybe is something quite small, I believe a same approach will work. But the hard part is like the gap between this can be large. So that will be hard. Then I will stop here. Thank you everyone for listening.
Thank you very much. Let us thank the speaker. Are there any questions?
I'm just curious, Songling, does it make sense to ask for, like, if you add a condition that the graph is triangle free, or actually have a triangle, I guess. Does it have to have a triangle?
So because like in the whole proof, in the nowhere didn't use anything about triangle, so I don't feel it's quite like. Maybe we can get some additional properties from the graph being triangle free, but at least like using my approach, I didn't see any advantage of not having a triangle.
Okay.
Yeah, may I also ask a question? It seems like most of, so could you maybe just briefly say which parts of the proof use the quasi-randomness assumption? It seems like it was not used in too many places, right?
Yeah, it's used in two parts, like in the third step, right?
Mm-hmm.
So for the first, like in the first step, when I do the switch of this pair, so this is vertex, this is a pair of vertices that missing the same color. So I know that as long as you have enough degree, so it is have an incident to an uncolored edge in the middle, and this one is incident to an uncolored edge in the middle. So I needed to make sure that well, actually, as long as you have bigger degree, and we did the first coloring, like it's kind of equalized. So every color is missed, not at too many vertices. It's possible to find an edge like in here and in here, right? So we can also have this size to be big. And the part I use the quasi randomness is because it's two sides big. I know that I can find an uncolored edge in the middle. This is one part. Right, and the second part, like in the second step, so when I found the matching, right, so I took off some vertices. Those vertices, they all saturated with the color, and in the remaining part, I need to find a perfect matching, and this is guaranteed by the quasi randomness.
I see. I'm curious, what would happen if you started with just some graph and try to apply like regularity lemma or something to split it into these quasi-random pieces? And
yeah, I think it's quite possible. It's just I didn't do anything like that. It's like in this this is kind of like a small version of the regularity lemma, but I don't know how to deal with all of the edges. But if you apply the ordinary regularity lemma, like we have some of those residues, so you may have edges there and have some other edges. It's kind of I don't know like how do you deal with those extra edges.
But you think that if say you happen to have an epsilon regular partition without exceptional pairs or something like this, then
yeah, that would help.
That's interesting.
Yeah, so I really think it's like for the second question here, right? If we assume the degree minimum degree is big, probably regularity lemma will help.
Yeah, interesting. I see. Thank you.
Thank you.
Are there any more questions? Okay, if there are no more questions, then let us thank Songling again.
Thanks everyone for listening.